In this section, we're going to discuss rational functions. As you can see on the screen, right now I've got graphs of two very basic rational functions. And before I get into the tables and the graphs of those functions, what I want to do is just cover some bullets about rational functions. So if we come over here and look at some of the notes that I have, and I'm just going to highlight my way through this and come up with some additional material here, and then we'll get into the graphs. If we look at the first part, if we look at the top, it says rational functions. Rational functions are quotients of polynomial functions. And we have a bullet here. It says f of x equals p of x divided by q of x, where q of x cannot equal 0. All right, so that's basically a textbook definition, a little synopsis of a textbook definition. And what does that mean? What is that more, how can we come up with a more layman's view of what that is? So very simply, all this is saying is if we had a function, polynomial function, very simply, if we said p of x equals x, if we created that function and we had another function q of x, and we'll make another easy function, x plus 1. So basically, both of these functions are linear functions. And if we wanted to create, now these are two separate individual linear functions. And if we wanted to create a third function, f of x equals, and that's basically what I have over here. If we wanted to create a rational function, f of x would just be the quotient or the division of both of these functions. So a rational function is nothing more than the division of two polynomial functions together. All right. And in this case, if we come back over here, I made a note. It said q of x cannot equal 0. And q of x is essentially my denominator in these examples. Well, in this example, we have this. We have x plus 1. That's my denominator. So we have to exclude any values of x that would make the denominator 0. And if you looked at it, now the only number that would not be allowed, if you looked at it very quickly, the only number you couldn't plug in for x would be x equals negative 1. Because if we did x equals negative 1, if I just wrote it out, used full function notation here, if we did f of negative 1, we would have negative 1 over, and then this would give us negative 1 plus 1, all right? So if I just carry this down, we'd get negative 1 over 0. And we know we can never divide by 0. That would, create an undefined situation, and then we would have to exclude that value from our domain. So that's all this is saying over here when it says q of x cannot equal 0. Basically, any value of x which makes the denominator 0 has to be excluded. So in this, quick example that I made, the only value that would have to be excluded is x equals negative 1. All right, so if we look at the next bullet, it says the degree of the denominator has to be at least degree of 1. So when I said earlier, rational functions are quotients. Quotients imply division. Not every function that has division is going to be constituted as a rational function. So we looked at these two. Look at this first example. It says f of x equals 4 over x. Well, in order for this to be considered a rational function, the denominator has to have at least one variable in it with at least degree 1 in it. And this one does. So you have 4 over x. So basically I have a linear function in the denominator. So that would pass the test. I have a variable in the denominator and it's at least degree 1. So this one would actually be okay. If we looked at the second one now, if we came down to g of x, and I looked at the denominator here, I don't have a variable in the denominator, I have a constant term, and we know that any constant term is always degree 0. So in order for it to be considered a rational function, it has to be at least degree 1. So for our purposes in this example, this one would not constitute a rational function. Okay? So not all functions that involve fractions are created equal, and they're not all rational functions. The very last example, or the last bullet I have over here, is going to deal with domain. And domain is an important, concept to be aware of in any function, but especially with rational functions. All right. So it says the domain of rational functions is the set of all real numbers except those x values which make the denominator equal to 0. So our domain is all the x values that we can substitute into the function except those which make our denominator equal to 0. All right. And if you look at the example I have below it, now this one's already nicely factored. And one of the things that I'm going to say as we go through the full examples in this section, as we do the graphs and as we find all the asymptotes and the intercepts, the very first thing you're going to do in all of these examples is make sure that you factor everything completely. All right, I'm going to hop on that as we go through this. You have to make sure when you're dealing with rational functions, you really want to make sure everything is factored as completely as possible. And if you look at the denominator, that's factored. Now, the numerator, we can't really factor that, but the denominator is nicely factored. And what we want to do is to find your domain. All you're going to do is, after you factor it, is you would set these factors equal to 0. If I do it over here, we would have x equals 0, we would have x minus 2 equals 0, or x plus 5 equals 0. And then you just solve for x. Well, the first one is already solved. And then for this one, all you would do is add 2. So we would have x equals 2. And then subtract 5. So we would get x equals negative 5. And actually, these would be x does not equal these values, right? We do not want x to equal those values. So all of these values, these three values are values that we would have to exclude from our domain. Everything else would be fine, but these values would have to go. And that's what I have over here with my domain identifier. It says the domain of function f is all x such that x cannot equal negative 5, 0, or 2. So basically, x is all real numbers except these three numbers. And that's what you have to do for rational functions. We're going to have to make sure, that we identify those values which make the denominator equal 0. And consequently, coming up, just as a little preview, any of these three values, we've got negative 5, we've got 0, and 2. At any of these values, that would give us, which we'll get into, a vertical asymptote. So we're going to have three vertical asymptotes in this graph. And we'll get into the asymptotes in a second. All right, so let's come over here to the actual pictures of the graph. Now, these two graphs are two of the most basic rational function graphs. These are actually reciprocal functions. They're rational functions, but they're the two most basic varieties of rational functions. And you'll notice that the rational functions, a lot of rational functions come in this variety. You'll see they have these two branch-shaped graphs, all right? And that's usually the way you're going to see them graphed out. And all I did to make these graphs was the most basic way to make a graph is to make a little table. And in each of the tables here, I've got 6 values of x. So if I was looking at the x column, and if I just took a couple of values, just to show you where these graphs came from, if we plugged in a 1, if we substituted in a 1, we would have x equals 1 over 1, so we have 1. So there is my pairing 1, 1. So I would have this point right here on the graph. And then if I just did it over here, if we did f of 2, we would have f equals 1 over 2, or 1/2. And there's my pairing over here. So that will be this point right here. All right, and so on and so forth. And then the same thing holds true for the square, the reciprocal of the square function down below. So if we did this, if we just, substituted a couple of values in, if I scroll this up a little bit, if we did f of 1, we would have 1 over 1 squared. So that's basically 1 over 1 is 1. And there's our pairing right here. And then just one more over here, we would have f of 2. So we would get 1 over 2 squared. And that would give us 1 over 4. And that's basically how I got these, how I made these tables. All right. And then you'll notice that we can substitute any value into this table, except the only value you won't see allowed in this table is x equals 0. Because just as, we just had the discussion about undefined cases over on the right when I went over my bullet points. In both of these cases, if we plugged in a 0 here, I'll just do it in this first one. If we did f of 0 here, we're going to get x equals 1 over 0. Well, we know we can't divide by 0 because we're going to get undefined. And then the same thing would happen in the denominator on the second one. We would get f of 0 here. We would get 1 over 0 squared. And that also would be 1 over 0. So in both of these cases, we would have an undefined situation when x equals 0. Okay? So the only value that's not allowed in the domain is actually 0. So we would say x could not equal 0. And if you look, if I scroll back over here quick, that little discussion I had at the end of the bullets, I said these three values created vertical asymptotes. So any value which makes the denominator 0, but not the numerator, is going to create a vertical asymptote. So we would have, actually, on our graph, we would actually have, if I highlighted it here in yellow, we would have a vertical asymptote on the y-axis. So these graphs would get infinitely close. If we kind of got as close to 0 as we could, these graphs would get infinitely close to the y-axis, but they would never actually intersect it, right? And this one would approach it from the right side, and it would go off to positive infinity. And then this one down below here, if we took a little point over here and rode the graph down, got really close to 0 as far as we could, this one would actually go to negative infinity. So if we were in this area here, if we approached 0 from this side, if we approach 0 from the left side, and when we say left side, all that means is we just put a little minus sign, all right? So as we approach 0 from the left side, and you see I'm approaching it from the left, I'm actually on the left side of 0, and we're coming in as close as we can get to it. What's happening to my graph, the actual line of the graph, and the line of the graph is f of x. As we get closer and closer to 0 from this side, f of x, and I'll do it like this, f of x is going to approach negative infinity. Okay? And in the upper part, so now I'm in this region, if we got closer and closer to x this way, if we got closer and closer to x from the right side, as if we wrote it like this, we could say x approaches 0 from the right side. The plus just means from the right side. F of x, the line of the graph, and I'll just show you again quickly, the line of the graph is going to approach positive infinity. Okay? So those are just some things to keep in mind with infinity and negative infinity. We're going to get into that in a little bit with when we discuss vertical asymptotes. All right, so that's basically the general shape of these graphs. They're not always going to look exactly like that, but in a lot of cases, you're going to see these branch structures, these opposing branch structures, and they have a variety of different shapes. So the next thing what I want to do is, in the handout, is we're going to talk about vertical asymptotes. It says vertical asymptotes occur at values of x which make the denominator equal 0, but not the numerator. I've kind of already alluded to this, but I wanted to, we're going to get a little bit more into detail on this. So at all these values here, I just want to erase this vertical line here. You can see the vertical lines are in all diagrams. At these points A, at all these points A, you see a vertical asymptote. So at that point A was some x value, you can see it here. It was some x value which made the original function's denominator equal to 0. So if we were to take a point, if we were to just pick any point on this graph, let's pick this one, okay? And it says the limit, and when you get more into dedicated lessons on limits, especially in calculus, they'll get more into detail, and it's just more of a cursory view of limits. So what this is saying is the limit. What is the graph itself approaching, the line of the graph approaching, as x gets close to A. And you see the little plus means from the right side. So if you look, I'm over here, I'm on the right side of A, and as we get closer and closer to A, and if I stay on my line here, I have to stay on my line like a road, like a railroad track. If I try to get close to A on the x-axis, I'm actually going to go up the line, and it's going to get really close to that dotted line, but it's never actually going to intersect it. And as we keep going closer and closer to that A, or vertical line, this graph is going to keep going up to positive infinity. So the way that we would write this is, it would say that what is the limit of f of x as x approaches A from the right? And the answer is just positive infinity. Okay? And then similarly, we're going to do it on the other side. So I picked a point, now I'm on the left side of A, and we have a different limit. It says, what is the limit of f of x as x approaches A from the left side? You see that little minus sign? The minus sign just means I'm coming in from the left side. So here is the line, right? Here's my dotted line of A, and I'm on the left side of it. What happens as we come into A, as we get close to A from the left, where does my line go? Where does my graph go? And it's actually going to keep going up to positive infinity, right? So that would be the limit. And that's really all that is. And then, on the bottom, same thing, but actually we'll wind up going to negative infinity. So what is the limit if we're down here? What is the limit of f of x as x gets close to A from the right? Well, here we are. Let's pick another point here. We're right there, and if I'm on the right side of A, so I'm coming into it from the right, I'm going to the left. What happens as we get close to A? I have to keep riding my line here. As we get close to A, that graph is actually going to go to negative infinity. So as we get close to A from the right side, it's going to go to negative infinity. And the same thing is going to happen on the graph, or in the graph on the right. If we pick another point here, let's just pick that point. This time, it's saying what is happening to the limit as x is going to A from the left side. And that minus sign just means from the left. So I'm on the left side of A, and we're going towards it. But as we go towards it, we're actually going downwards, and we're going to keep going downwards, and we're going to approach negative infinity. Okay? So that's basically what happens with vertical asymptotes. The graph is going to get, it's going to approach some value that it can't actually equal, and it's going to wind up going to positive infinity or negative infinity. And that's really all we're saying here. So if we come down here, it says, so as x approaches A from the left or the right, f of x is going to wind up approaching infinity, actually positive infinity or negative infinity. And that's really all a vertical asymptote is. It's going to get close to a value, but it's never actually going to equal it, because it can't equal it. Otherwise, it's going to create an undefined situation. And it's either going to wind up going to positive or negative infinity. It's really all it is. All right, so what I have next is, this is the more mechanical part of this. So these are the steps in finding your vertical asymptotes. And this is where I want to end the lesson today. So to find the vertical asymptotes, you have these 4 steps. And I've kind of already alluded to that earlier, but you can see all the steps. And in my lessons, you'll see I like to step everything out, so you guys have a concrete method of doing the material. So the first step in finding vertical asymptotes, and you heard me say it before, it says you want to factor the numerator and the denominator completely. So factoring is key. Second step is going to be cross out any common factors. The next thing is going to be set remaining factors in the denominator equal to 0 and solve. And any answers that you get are going to be where the vertical asymptotes are going to occur. These are the values, and I'll circle it right here. It says these are the values which make the denominator equal 0. So just doing a couple of these examples, I'm going to leave this up for a little bit. I'm going to do this first one. I'm going to leave the steps up for the first one. So the first step, if we come up here, it says factor the numerator and denominator. So I'm going to do that. Well, it looks like, if I write this out, it looks like my denominator, actually going to move this up just a little bit. First step is going to be factor. Well, the numerator is pretty much set. There's not much I can factor out of the numerator. The denominator, you can clearly see that we can factor out an x. So if we factor out an x, what's left is, if we take an x out of 3x squared, we're left with 3x. And if we take the x out of 7x, we're left with a 7. Okay? So that's the first step. First step is to factor. Second step is, we come over here, second step is to cross out any common factors. Well, if we write this out, f of x equals, and if we cross out common factors, you can clearly see we're going to cross out the x's in the numerator and the denominator. So what's left? After we cancel those, we're going to have 1 over 3x plus 7. Okay? Next step, if we come back up, it says set the remaining factors in the denominator equal to 0. So the third step is going to be, well, I only have one factor in the denominator. We're going to set that equal to 0. And then we're going to solve. So if we subtract 7 here, we're going to get 3x equals negative 7. And then you're going to divide by 3. So in this example, we're going to have a vertical asymptote. If we write it out, we're going to have a vertical asymptote at x equals negative 7/3. And that's all that is. Those are the four steps. So any value that we find where x equals some value in my denominator, that's going to create a vertical asymptote. Let's look at B. So the 4 steps, if I wrote it again, wrote it over here, the 4 steps would be to factor. Right? Now we've got some factoring work to do on B. So this one is going to factor into, it looks like it's going to factor into x minus 2 times x plus 1 over, and this one looks like it's going to factor into x minus 2 times x minus 1. Okay? So that should be the proper factorization of the numerator and the denominator. Remember, you want to factor everything first. All right, that's just how that one's going to work. The next step is we're going to cancel. So you're going to cancel your common factors. And it looks like in this one, it looks like we can cancel out the x minus 2's. And whenever you're canceling out common factors with these rational functions, it makes life a lot easier because we're always going to work with what's left over. We're going to work with the reduced or the canceled polynomial, canceled rational function. So I have this. I have f of x equals x plus 1 over x minus 1. And then the third step is you want to set your denominator equal to 0, okay? Because that's what's going to create our vertical asymptote. So we have our denominator as x minus 1 equals 0. Or you could make it not equal 0. It doesn't really matter there. And then we're just going to solve this, right? That's going to be the 4th step. So we would solve this, and we're going to add 1, and we're going to get x equals 1. So at x equals 1, we would have a vertical asymptote. And then that would be a piece of the puzzle of creating the rational functions, or graphing the rational functions. Now, rational functions have a lot of different pieces, or they potentially could have a lot of different pieces in them. So this is one of the pieces, the vertical asymptote, that could be part of them. All right, the very last one. Now, this last one, I'm going to just keep my steps over here on the right, so we're going to move this over. And what I have, and again, first step is we're going to factor. Well, the numerator is a difference of cubes. So if you remember how to factor a difference of cubes, and this one actually should be, it's kind of not written there, that should be f of x equals. So if we factored the numerator, this would be f of x equals, to factor a difference of cubes, this would factor into x minus 3 times, and it's going to be x squared plus 3x plus 9. Okay? So the second set of parentheses would factor into x squared plus 3x plus 9. And then my denominator is actually, if we look at this, this is actually just a difference of squares, and that's going to factor into x minus 3 times x plus 3, okay? So now it's factored. Step 2 would be to cancel your common factors, and you can clearly see that the x minus 3's are going to cancel. So what I have left is f of x equals x squared plus 3x plus 9 over x plus 3. And then for step 3 is we're going to set just the denominator equal to 0. So if I took this over here, we would have x plus 3 equals 0. And then we're going to solve. So all you're going to do is subtract 3, and we're going to get x equals negative 3. So that would create a vertical asymptote. Okay. So at this point, I think I want to end the video, and I just want to do a quick little check, a little rehash of some of the things we talked about. We went into the intro of what rational functions are. We went over to some bullet points of how they're comprised. We went over what the degree of the denominator had to be. We talked about domain, and then we went over the tables of how they're calculated, and then we also went into some discussion on vertical asymptotes. And then what I did was I went over some steps on how I like to find, more mechanically, how I like to find the vertical asymptotes. So hopefully that all made sense. Hopefully you enjoyed the lesson. And stay tuned for part 2, where we'll talk about holes in the graphs of rational functions. We'll talk about horizontal asymptotes, slant asymptotes, and then we'll get into some graphs. Okay, so take care.